So this is the first activity where we're starting to both come to grips with the notion of what a function is and how a function describes a particular kind of relationship between two quantities, right? And also beginning to use some of the mathematical terminology that relates to functions. And that, I think, is where those are the places where it tend to cause the most question marks. So just looking at the 40,000-foot view of this problem, in this problem, we're relating together the height of water in this spherical tank to the volume of water that's inside the tank. And what we know about the tank is that it's a sphere and that it has a radius of 4 feet. So the first question asks us, what values of h could even make sense, practical sense, in this context to consider? What are the limitations? What can h be and what can h not be? Yeah? 0 to 8, yes. And so when I was going around to the groups, if you said something like that, I said to you, just write that sentence down, because that is an adequate answer to this question, right? H from 0 to 8. So why can we not have h's that are outside of that range? The height of the sphere is 8 feet. So we can't have 12 feet deep of water in this 8-foot tank, right? And what about the negative values of h? Why do we throw them out? Yeah, it doesn't really make sense to say that the water is negative 2 feet deep, right? Because h is measuring a physical distance, we tend to use non-negative numbers for that. Right. So notice that the answer to part A is not a number. It's not an expression. It's not a function. It's not anything else. It's what we call a set, right? It is a whole bunch of numbers. How many? How many numbers are there between 0 and 8? That's how many whole numbers there are between 0 and 8. Yeah, don't forget the decimals, and don't forget the things that are not even decimals, they're irrational numbers. How many are there? Infinitely many, right. So we could never possibly write them all down. So what we're describing here is a set. A set is a collection of objects. In this case, the objects are numbers. And so that's the kind of objects that we're going to use to answer this question. It's the set of all real numbers between 0 and 8. We could use notation to write that down if we want to. Maybe this is a good time to do that, right? So I'll just answer part A here. So there are a couple ways to do this. One way is to say, well, the smallest value that h can have is 0. The largest value it can have is 8. Is there a way that I can sort of use symbols to describe this set that I'm talking about? Yes. So there's one way to do it, right? We could use an inequality to express this, right? We could say the h's that we are permitted to consider are between 0 and 8. And so if we use inequality symbols, we would put a less than or equal to here and a less than or equal to there, right? By the way, we should check. How do we know that equal to is okay? Why does it make sense to have h be equal to 0? What would that mean for my tank? Totally empty, right? So h equals 0 is still meaningful. H equals 8, what's happening with my tank? Totally full, but that's still okay, right? So less than or equal to is okay to use there. But really an inequality is not a set, so to speak. It's just an inequality. So what we often will do is add notation around it to say what we're talking about is the set of all h. I'll put an h there. And then we'll put some separator in between here. Sometimes it's a colon, sometimes it's a vertical line. I don't really care which one you use. But when we read it in English, we'll say such that the set of all h such that h satisfies the inequality 0 less than or equal to h less than or equal to 8. Does this notation look familiar to people from some distant memory? Or maybe not so distant if you took a pre-calculus readiness class last semester. Right, so this is another way of describing it. And there's one more, a more compact way of writing the same thing. What about interval notation? What would this look like as an interval? Put a 0 and an 8, the lower limit, the upper limit, comma in between them. What do I want to put on the ends here?
Brackets.
Brackets. Why brackets and not parentheses?
Because it can be equal to.
Yes, because equal to is okay. We're including 0 and we're including 8. And so we use the square brackets instead of the round parentheses. Right. So those would be ways of describing a set. the set of all h's that satisfy this inequality, or the interval of real numbers that goes from 0 to 8, inclusive of 0 and inclusive of 8. Thank you for the correction. The units are cubic meters and meters, respectively. Right. So the smallest value of the height is 0 meters. The largest value that the height can have here is 8 meters. Say again?
4 feet.
4. And the radius, yes, thank you. One more place to correct. 4 meters. Yeah. I feel like in the previous sections, we did use imperial units instead of metric. So I was sort of, I didn't read closely enough, which do as I say, not as I do kind of thing. Okay, so then my follow-up question is, what's being asked in part B? What is the domain of the function f in the context of the spherical tank? What does domain mean? X values, but which X values? The inputs. X values are what we mean by inputs. But what is domain asking? Which X values is it asking for? Well, in this example, the x coordinate, the input variable here is the height h. But when the question asks you what is the domain, which input values are we concerned with?
The ones we just gave, 0 through 8.
The ones we just gave, 0 through 8. The domain is an answer to the question, what are all possible inputs that we want to consider for this function? So now we're talking about inputs, which means that we've sort of turned a corner here to start talking about what a function is. So when we think about inputs, what picture do we have in your mind of what a function is? Because this is the one that I tend to have. We have a little machine, and it's the job of this machine to kind of, take an input in the top and spit out some output here at the bottom, right? So I put in to this function, nope, I don't want to call it h. I want to call this something else. I'll call it f. That's what we end up calling it later, right? We put a height into this function, and it spits out a volume. So that's kind of a schematic diagram. This is, if you're thinking like a computer scientist, this is what you might think of as being a function, right? A function, when you program a computer, is just that, right? It takes in an input, it does something with that input, and then it spits out an output, right? So this function f, its job is to turn a height into a volume. Now, what is it that makes that a function as opposed to some other type of relationship? What do functions have to do that other types of relationships don't necessarily have to do? What's special about functions? Every input that we put into this function has an output. How many outputs?
1.
Just one. Yes. That is what makes a function a function. Not only does every input give me an output, the same input is always going to give me the same output. If I put 4 into this function, it's going to spit out some number. If I put 4 into this function again, it's going to spit out that same number again. It's not ever possible for me to ask a function the same question and get 2 different answers. Right? If I give it the same input, it's always going to give me the same single unique output that's associated with that input. Every input has only one output for a function. That is what makes functions functions. And the domain is an answer to the question, what are all possible inputs that we want to consider for this function? So what is the domain of the function in this context?
0 to 8.
0 to 8. It's the same as our answer to question A, right? It's this set, the set of all h's, such that h is between 0 and 8, inclusive of both. Right? Okay. And those are the values of h that make sense to consider in the context of this function. What about v? What are the values of v that make sense in this context? So that was also asked in part A. We didn't talk about it yet. Now's a good time. What values can v take on? 0 to whatever that 260, Right, so when h is equal to 8, right, you plug that into here, you get, right. So let's get that number here real quick. So when the tank is totally full, right, the volume is going to be f of 8. That's how we would read that, right? It's the output when the input is 8. How did you find f of 8? You find the volume of the sphere, or equivalently, you use the formula that we're given that not only tells us the volume of the whole sphere, it also tells us the volume of the partially filled sphere when we know what the height of the water is, the depth of the water. So how do I use this formula to tell me that volume of the whole sphere? Yeah, replace h with 8. Because when the depth of the water is 8 meters, that means that this spherical tank is totally full, and so we get the whole volume. So, right, there is a chance for us to use the equation that we're given here. Pi over 3 times 8 squared times 12 minus 8. 8 squared is 64. 12 minus 8 is 4. Multiply those is 256. So that's 256 pi over 3. Now, I heard a lot of decimals walking around. Talked to a couple people who had questions about how we round decimals, when to round decimals. I can only muster so much passion to have conversations about decimals and rounding. I much prefer, whenever those questions come up, to say, if you write 256 pi over 3, you have a correct answer, right? Not only is it correct, it is more exact than any decimal that you could write down in that spot, right? So I'm okay with 256 pi over 3, but I also understand that from a human perceptual scientific perspective, if you want a decimal to help us understand sort of roughly how big that number is, feel free to get that decimal, but wait until you get to your final answer here, plug that into your calculator. Rather than plugging something in earlier, rounding off pi to 3.14, or any of that kind of thing, right? Wait until you have your exact answer and then estimate it, and you get 200 and something, right? Right, so how would I write my answer to that? What values of v make sense?
F of 0 is less than or greater than v is greater than or less than v.
Yeah. So I would say that's a set of all v's such that v is greater than or equal to 0 and in turn less than or equal to, I'll just write 256 pi over 3. If we wanted to write that as an interval, we could also write that as an interval, right? 0, comma, 256 pi over 3, with, again, brackets on both ends, because both of those are included. Okay. So what is part B asking when it says, what is the corresponding codomain? Right, and that actually was the Twitter fight that I had with my colleagues yesterday. Is it the same thing? Does codomain and range mean the same thing or different things? Should we care, particularly if we're in a pre-calculus context? And the argument got extensive. Not rancorous or anything, but people had a lot to say about how they thought about this question. And this is kind of how math teachers, this is how we be, behind the scenes, right? We're teaching this thing in our class. We didn't know how to answer this question, and so you see things happening in here where we're reaching for like higher mathematics to try and answer this question to our own satisfaction. What I would say, I think where we ended up in this discussion, is we ended up at the stance that the codomain and the range really do mean different things, so they can mean different things. And they mean different things in the following sense, right? Well, no, why don't I do it this way? So if I take this function, this formula, f of h equals pi over 3, h squared, 12 minus h, if I just graph that thing, right? If I just open a Desmos grapher and ask for a graph, this is what the graph looks like, right? And it kind of has this quality to it that we would have expected based on our previous discussions, right? When the height of the water is 0, the volume is 0. That makes sense. The tank is empty. When the height of the water is 8 feet, so I guess I do have to zoom out on this a little bit. When the height of the water is 8 feet, we would be right there. And notice the relationship between volume and height has this nice little sigmoidal shape that we predicted in our last class. It should have. Great. But if I just graph this formula, I'm seeing too much on this graph. Why is that? What do I mean? If I just write down the formula that I wrote down here, there's nothing mathematically that restricts the values of h to just be from 0 to 8. Any number, h, any real number that I pick, I can put into this formula and get out a number for v. Right? And so what are the set of all h's that we can consider here in this abstract formula? What values of h are possible? All of them. Right? Not just from 0 to 8, but from minus infinity to infinity, right? And so what I might call that, I'm going to try to be careful about this, I'm going to call that the maximal domain for this function. That is the largest set of h's that I can plug into this formula and get a reasonable answer, right? Get a number popping out. Maximal domain, h can be anything from positive infinity to negative infinity, everything in between. And one way of understanding that from this graph is that we're going to get a graph that covers every single spot on the horizontal axis. Every single value of h that I could pick corresponds to one point on this graph. Right? One way of understanding the domain of a function is to just take its graph and squish the graph down onto the horizontal axis. See how much of the horizontal axis is covered by the graph. And this graph extends all the way to the right horizon and all the way to the left horizon on the xy plane. So every real number h is part of the maximal domain for this. Now, the practical domain, which is what we're just going to call domain here, that was informed by our choice that this h represents the height of water in that spherical tank, right? And so the actual domain that we care about for practical purposes in this problem is just the h's from 0 to 8. And so just that portion of the horizontal axis, which I'm going to try to shade right here. There we go. So that interval from 0 to 8, that's our practical domain. That's the domain that we actually care about when h and v are meaningful the way that they are in this problem. But mathematically, this formula has no restriction on what h's we can put in. Does that make sense, that distinction between sort of all of what's possible and all of what sort of we care about, right? The smaller set that's more practical. Would there have been a way for us in the formula to specify that we only wanted h from 0 to 8? There are some really nasty, arcane ways we could do it with algebra, but it's probably not what you're asking. We could do it, but it's much, if you want to do it in Desmos, the way you would do it is just use these curly braces and then put your inequality, 0 less than or equal to h less than or equal to 8, inside of those curly braces. And now look what happens, right? It only gives us that portion of the graph that now has the domain, h going from 0 to 8. So if you're interested in making Desmos cut down your graph so that it has the smaller domain that you want, as opposed to just having its maximal domain, which it will do otherwise, then that's a way to do it.
I was actually interested in the algebraic way, but if we don't have time.
Yeah, we can talk about that another day, perhaps. It's much less illuminating, I think, than.
I imagine.
Yeah, it's kind of nasty. Well, what we would have to do is we would just have to write down a function which is equal to 1 when h is between 0 and 8 and is undefined anywhere else. That's kind of hard to do, but it would kind of look like a stair step, right? A little table, a little horizontal line at 1, but then undefined. Yeah, so there are ways of doing it, but it's not. Yeah, it's not. I don't even find it particularly, it's kind of one of those cool tricks that you see done once, and then you're like, okay, I'm not ever going to do that again.
Yeah.
Right. And so we got into this discussion because we were going to talk about codomain versus range. And I would say the same sort of comment about codomain and range. If we're just thinking about what values this function can take on, what values v can have, I take the whole graph and I squish it onto the vertical axis. How much of the vertical axis does it cover? It's a little bit harder question. But if we were to zoom out on this graph far enough, remove this domain restriction here. If I zoom out, how much of the vertical axis is this graph actually covering? The whole thing, right? Negative infinity to infinity, once again, right? So that is what I would call the codomain of this function. It's like the maximal range is another way to think about codomain. One of the people in the Twitter conversation, Dr. Kate Owens at College of Carolina, she said it as, she thinks of the difference as being like the places that I've traveled to in my life are the range. The places that I could travel to in my life that I haven't maybe yet, that would be the codomain, right? So it's this difference between the possible and the actual, between, idealism and pragmatism or whatever. It's one of these classic kind of questions. So the codomain, I'm going to think of this, we can think of this as the maximal range. And in this example, that would be minus infinity to infinity. Whoops. By the way, we never use a less than or equal to with infinity because infinity is not a number. So v cannot equal infinity. But it can be anything, any real number at all, right, is part of the codomain. But what's the range? These are the values of v that correspond to the values of h that we actually ultimately care about. Right? When h goes from 0 to 8, what does v go between? What did we decide?
0 and 256 pi.
256 pi over 3, right. So let's locate that on the graph real quick. So v equals 0 is right here. Right? V equals 0 is the origin. And then, whoops, how do I go backwards? Uh-oh, where did my stuff just go? and then v goes up as high as 256 pi over 3, and that would be this point here at the other end of the domain, right? This point there at the top, that would be my 256 pi over 3. So it's what I get when I squish that portion of the graph that lies above my domain. I squish that onto the vertical axis, and there's my range. So these are sort of the most important data that we can know about a function, even without looking at its specific formula and all the different properties that functions have. That's what we're going to do all semester. That is the story of pre-calculus. But before we do any of those detail looks, right, we have to know the basics about a function. What kinds of input can it take, and what kinds of output does it produce? Right? If you're a computer scientist, you ask this question every time you write a function when you're coding, right? And the domain and the range are the answers to that. Where the domain and range specify, for our purposes, we get to make this choice, kind of, right? What inputs do we want to care about? And then what outputs are generated from those inputs that we care about? That's the domain, that's the range. And again, on a graph, that's just what portion of the horizontal axis is being covered, what portion of the vertical axis is being covered, that we're making the choice to cover. The maximal domain and the codomain, those are things that do get dictated by the mathematics, right, by the particular form of this function. And the fact that any number, any real number h, we can plug into this formula and get a value for v of h. So the maximal domain includes all values of h. And when we look at the graph, we see that all possible real numbers v are also produced as the output of this function when h is allowed to range over all real numbers.